In this fifth part of the flight control series, we will operate the spoilers. The Boeing 777 has 14 spoilers. The left wing has 7. 5 outboard. And 2 inboard spoilers. Likewise, the right wing has 7. 2 inboard. And 5 outboard spoilers. Spoilers serve two purposes on the aircraft. They assist the flaperons and ailerons during roll control. They also act as speed brakes. Each spoiler is connected to a power control unit. The PCUs are hydraulic actuators and use different hydraulic system of the aircraft for redundancy. For the PCUs to actuate, they need input signals, and there are 4 possible sources. The roll signal can be given by using the control wheels, or by the autopilot computer, and the speed brake signal can be manual, or automatic. The auto speed brake system will not be covered in the flight control series. Let's start with the control wheels. As we saw in the previous chapter, when the control wheels are rotated to give a roll command, the position transducers send the wheel position signal to the flight computers. The control wheel rotation also sends a mechanical signal through cables. The mechanical signal will directly control number 4 and 11 spoilers. The electrical signal is processed by the actuator control electronics and transferred to the primary flight computer. The PFC informs the ACE to deflect the flaperons and the ailerons. It also informs the ACE to operate the spoilers. The ACE will now electrically open the control valves on the spoiler PCUs. On the left wing as the flaperon and aileron deflect upwards, the spoilers move up. On the right wing as the flaperon and aileron deflect downwards, no control input is given to the spoilers on the right side. During roll command, the number 4 spoiler on the left wing is not fly-by-wire controlled. It is operated by the mechanical cable connected directly to the control wheels. The cable movement opens the PCU hydraulic valve and the spoiler moves up. When a right roll command is given, the fly-by-wire controlled spoilers on the right wing deflect up, and the left wing spoilers are not controlled. The number 11 spoiler will move with the mechanical input from the control wheels. Next, the autopilot input, resulting in spoiler deflection. The autopilot computer requests a roll command to the primary flight computer. The PFC will send 2 calculated signals, one for the ACE to move the control surfaces, and the other for the autopilot computer to back-drive the control wheels. As the ACE moves the fly-by-wire controlled spoilers and other surfaces, the autopilot computer back-drives the control wheels. Control wheel rotation will move the mechanically controlled number 4 spoiler. Once the autopilot command is over, the surfaces and the control wheels will return to neutral position. Finally, let's see the speed brake control. The speed brake lever is used to deflect the spoilers. The lever has 3 positions. Spoilers down, armed for auto speed brake, and up for manual control. Selecting the lever to the up position will move a clutch assembly. The change in position is picked up by the transducer. The position transducer sends signal to the flight computer through the ACE. The PFC commands the ACE to move all 14 spoilers to their maximum deflection. During aircraft roll command, the control wheels give the mechanical signal to the number 4 and 11 spoilers, which is not possible when using speed brake lever. Therefore, during speed brake extension, all spoilers are fly-by-wire controlled, including number 4 and 11. Since we have covered all the primary flight control surfaces of the aircraft, next part, we start with the high lift devices. Thanks for watching. Two flight control surfaces are part of the high lift control system: the leading edge slats and the trailing edge flaps. In this 6th part of the series, we will understand the flap mechanism. The 777 has 4 flaps: 2 single-slotted, outboard flaps, and 2 double-slotted, inboard flaps. The flaps are fly-by-wire controlled, and has 3 modes of operation. The flap position is controlled by using the flap lever. The lever has multiple positions, for different slat and flap configurations. Position transducer keeps track of the current flap lever position. Change in lever position causes the transducer position signal to change. The signal is received by the flap slat electronics unit computer. The flap computer engages the primary mode. Flap lever position 1 results in slat movement. Since we are interested in trailing edge flap movement, let's skip to flaps 5. In position 5, the computer will operate the flap power drive unit. Signal is sent to the hydraulic control valve. Aircraft center hydraulic system pressure is used to operate the flaps. The valve opens to run the hydraulic motor. The motor turns the PDU gearbox, connected to the torque tubes. The torque tubes will now drive 4 transmission assemblies on each wing. The transmission assemblies rotate the ball screw using the torque tubes input. The torque tubes cannot run straight from the power drive unit to the last transmission assembly. Therefore, tubes are rerouted with the help of angle gearboxes. Of the 4 transmission assemblies, 2 will move the inboard flap. The other 2 will move the outboard flap. Let's see how the transmission assemblies extend the flap. The ball screw rotation moves a nut. The nut is connected to the drive arm. The drive arm moves the carrier beam, and the flap extends. Flaps 15. Similar mechanism extends the inboard flap. Two position sensors, one for each wing, measure the torque tube rotation to help the flap computer determine the current flap position. Flaps 20. When a flap position change command is given, the position sensor signal helps the flap computer to stop the movement once the flap has reached the selected setting. The inboard flap is a combination of 2 parts: main flap and the aft flap. When the lever is selected to flaps 25, as the transmission assemblies extend the inboard flap, mechanical pushrod connections will deflect the aft flap more than the main flap. The final flap lever position 30. If the commanded flaps fail to deflect, due to hydraulic system failure, the flap computer will automatically switch to the secondary mode. In secondary mode, the FSEU will command the power drive unit electric motor to operate the flaps. The primary flight computer receives the flap position data from the FSEU. This allows the PFC to droop the flaperons and improve low-speed performance. The PFC also droops the ailerons in some flap positions. Now let's retract the flaps to the up position. Retraction process is similar to extension. Lever command is received by the flap computer. The computer will run the motor in the opposite direction. This will reverse the torque tube rotation and the flaps retract. If a flap computer, or any other component failure, prevents the system from working in the current mode, then the alternate flap switch can be used to extend or retract the flaps. The system must be armed before using the alternate switch. Arm switch will send a signal to the FSEU to disengage the current mode, and the computer will stop controlling the flaps. Let's continue flap retraction using the alternate switch. When the alternate switch is used, a direct signal is sent to the electric motor to retract the flaps. The switch must be turned off after flaps have reached the desired position. The next chapter will be on the leading edge control surfaces. Thanks for watching.